SwayamPrabha. Digital India. Educated India.
In this lecture, let us continue discussing about the governing equations of viscous high temperature flows, including the boundary layer equations. We would try to identify the similarity parameters when we look at the boundary layer equations. We would look at different forms of the energy equation, and finally, we will close the discussion by looking at the boundary conditions applicable for viscous chemically reacting flow. This is something that we had discussed in the previous lecture. It is a quick recapitulation of the governing equations for chemically reacting viscous flow. We had the global continuity equation followed by the three components of momentum equation. As you may recall that this can be quickly simplified or compacted into a single equation if you are using the index notation. Here we have split them apart so that we have a better look at the different components of the stresses. For example, we have the normal stresses, we have the shear stresses. This was discussed at length last time. Then we looked at one form of the energy equation where the total energy was considered, the substantial derivative of the total energy was considered, and followed by that we introduced the heat flux vector, including the effects of conduction, diffusion and radiation. Diffusion in particular is a major effect here because we have a chemically reacting gas mixture and you would have multiple species available in the mixture with different concentrations and therefore, possibility of diffusion of one species into the other. We had then looked at the species continuity equation in its different forms, both in terms of the substantial derivative and otherwise, and also considering the mass fraction, the mole mass ratio. Then we moved on to including the species concentration equation and then we looked at the condition of the energy for thermodynamic equilibrium, local thermodynamic equilibrium. This is where we stopped, and from there we pick up and we continue the discussion here, saying that if vibrational non-equilibrium is present in the gas mixture, then there is a procedure by which we have to calculate the energy related to vibration using this equation, where as you can understand there is an additional term. The corresponding equation when both thermodynamic and chemical non-equilibrium exist in the case of an inviscid non-equilibrium high temperature flow. The difference that is made is due to the inviscid nature, where the diffusion is absent and then you see that the equation basically shrinks to the two terms A and C. There is no presence of the diffusion term in the above equation. That is what we have highlighted over here. So, that is purely a viscous effect which you have to distinguish. Now, if you look at the significance of the three terms that we left behind in the previous slide, then the first term, the time rate of change of vibrational energy caused by species I per unit mass of mixture, followed by the next term, diffusion of vibrational energy as species I diffuses in or out of the fluid element across its boundary, and then the term C, the finite rate vibrational relaxation of species I. When we studied high temperature viscous flow earlier in the course, where if you recall, there we had taken it as a non-reacting viscous compressible flow. That was the context. The governing equations that were considered at that time included the global continuity equation, the momentum equation, energy equation, equation of state, etc. So, there are differences that we are seeing over here when we talk about the reacting viscous flow, and essentially what we are highlighting over here are the differences. So, the first difference is that we have the species continuity equation included for chemical non-equilibrium, either viscous or inviscid flow. So, it basically arises from here. Then comes diffusion, it is included in the species continuity equation and energy equation. Then comes the heat of formation at absolute 0 in the expression for internal energy or enthalpy. So, these are the primary differences that we see. Let us move on to some other forms of the energy equation. Here we consider the total energy, we look at the q vector, and if you move on to other forms, then you see total or stagnation enthalpy. That means you are moving to h plus v square by 2, which is coming under the substantial derivative here now. You have a time dependent term for pressure, then divergence of q, and a lot of viscous terms which are essentially products of velocity components and stress components. We need to take a note of this, that we have to use the relation h is equal to p by rho and derive a relation for dE dt in order to obtain the above equation. Next, an expression for the substantial derivative for v square by 2 can be obtained by multiplying the x, y and z momentum equation and adding them. That equation, when subtracted from the above equation for the substantial derivative of h naught, would give us an equation for substantial derivative of the static enthalpy. Therefore, from one form to the other, we need a few steps of transformation which takes us from one form of energy equation to another form. If you were to go through those steps, you would be able to derive this form for the energy equation, where we have the substantial derivative of the static enthalpy. From stagnation enthalpy, we have now come to static enthalpy. You see a very important term here which is called as the dissipation function, which comprises of different velocity gradients and stress components. You need to take note of the fact that the dissipation function will be a very bearing a very strong value in regions where strong gradients of velocities exist. In the above different forms of the energy equation, the internal energy, the stagnation enthalpy, the static enthalpy, all that we were considering were taken in the form of absolute values. They contain the effective 0 point energies in the form of heats of formation of the species. So, this is included in their definition. If you recall a few slides back, that is what we left behind in an expression for internal energy. Therefore, when the chemical reactions take place, the chemical energy exchanges occur during the reactions, then automatically the 0 point energies are accounted for. When you write down an expression for static enthalpy, for example, considering a diatomic molecule, then you see that the equation is written in this form. So, you have 7 by 2 RT followed by the vibrational energy, the electronic energy, and then comes the 0 point energy. Note that from the E equation that we wrote before, you can easily derive the enthalpy equation as well over here. The bracketed part is the sensible enthalpy, as we say, and the remaining part is the 0 point energy. For the mixture, you would have to account for all the species which exist in the mixture and would have to have a summation of Ci times Hi sensible and then Ci times the 0 point energy in terms of enthalpy summed over all the species. So, that would give you the H for the mixture. If we were to derive an expression for the substantial derivative of sensible enthalpy, then it will turn out to be in this form. And you find that in that the 0 point energy gets segregated out. In none of the expressions before did we see this happening. So, the above form for energy equation is in terms of the sensible static enthalpy. The equation contains a term on the right hand side which explicitly accounts for the chemical energy change during reactions. That is what we find over here. On the other hand, the previous forms of energy equation were all written in terms of absolute values, not the sensible values, where no term involving the delta Hf had surfaced explicitly in the equation. Therefore, when you consider absolute values, you would not see a term looking like this surfacing in the equation. When you write it in sensible values, then you see it surfacing explicitly. This is a major difference that you have to keep in mind. By looking at this alone, you can figure out in what form the enthalpy has been written. Boundary layer equations, let us look at them for a viscous chemically reacting binary gas mixture. So, as you know, we are now going to simplify the Navier-Stokes equations under the boundary layer approximation, where you have a very thin layer adjacent to the surface within which the viscous effects are practically confined, and the length scale associated with that thickness is way smaller than the characteristic dimension of the body by definition, and this would generally occur at fairly large values of Reynolds number. In high temperature air, the dissociated gas mixture is often lumped into heavy particles comprising of the molecules and light particles comprising of the atoms. Right in the beginning, when we start discussing boundary layers, since we are discussing it in the context of chemically reacting flow, it is a high temperature gaseous mixture where chemical reactions are taking place. We have to think about the chemical aspect of the boundary layer to begin with. This is not what we had discussed in the earlier part of the course, where we had a compressible boundary layer, but there were no chemical reactions in it. So, here we first of all categorize the heavy particles and the light particles comprising of the molecules and the atoms, and as far as oxygen and nitrogen are concerned, they are very similar in nature in terms of this classification, which is clear from a more detailed theory of kinetic theory of gases. For example, the collision cross section of these molecules are very similar. Based on that categorization into two classes, a binary gas mixture may be considered for simplicity, and in the case of a binary mixture, the diffusion coefficients which will be involved are very easy to define. There are two species, so two diffusion coefficients, namely D12 and D21 respectively. Now, we already learned this relation earlier in this week. So, if you apply it to the binary gas mixture, then you will end up finding a relation like this, where one species stands for the lighter one, the other species for the heavier one, and then we apply Fick's law. By definition, C1 plus C2 should be 1, and therefore, if you apply a gradient operator to this equation, you find that they are connected through a negative sign. So, if that is substituted here, you end up getting this relation that the diffusion coefficients are equal to each other. So, with this finding, we move on to the boundary layer equations. We are not going through a very elaborate description of the order of magnitude analysis of the Navier-Stokes equations. We go directly to the simplified form. We look at the global continuity equation, species continuity equation, the x momentum equation, and as you follow them, I hope you are noticing the different terms which are coming up in the equations. The y momentum equation, and finally the energy equation. Note that the energy equation that we learnt earlier as a part of the non-reacting compressible boundary layer, it looked like this, and the distinguishing term I think is already evident to you, that happens to be this diffusion term. Apart from that, they were kind of equivalent. When an order of magnitude analysis is performed on the energy equation in terms of the total enthalpy H naught, then we would find that the boundary layer equation form would be like this. Again you see the diffusion term figuring here. Again the energy equation can be expressed in terms of temperature, and that becomes particularly relevant when you talk about non-equilibrium high temperature flows, because as is evident, the chemical rate constants would be dependent on temperature, and therefore having the energy equation expressed in terms of temperature has its own advantage. Starting from the energy equation form written in terms of static enthalpy, the energy equation in terms of temperature can be derived for a boundary layer flow as follows. We are not going through the derivations in detail, but looking at the final forms. You see a CPF term coming up over here, which is the frozen specific heat, and you can go back a few lectures where we had briefly discussed about it. Hi is the absolute enthalpy for species I, which can be written like this. The first term is being evaluated based on the fact that we consider a thermally perfect gas in local thermodynamic equilibrium. The other part of course comes from the 0 point energy. So, this is basically the sensible part that you are working out based on the fact that Cpi is dependent on temperature. The non-dimensional groups are formed as follows to identify the similarity parameters of a viscous chemically reacting boundary layer, which of course over here has been considered as a binary gas mixture. And you recall that similar practice was taken for non-reacting compressible boundary layer earlier. However, some of the things over here are additional. For example, this was not there in the earlier case. So, we have non-dimensionalization of the length scales taking a certain characteristic length of the body, non-dimensionalization of other flow and thermodynamic parameters considering the conditions at the edge of the boundary layer, where the subscript E has been used to define the conditions at the edge of the boundary layer, which are used for the non-dimensionalization purpose. So, you will find each and every term getting non-dimensionalized in this way. Finally, when we substitute all this in the dimensional form of the energy equation, we end up getting the non-dimensional expressions, and then you end up finding some of these interesting similarity parameter groups coming up over here, surfacing over here. If you identify them separately, then the first one happens to be the Reynolds number, which was identified as one of the similarity parameters in non-reacting compressible boundary layer 2. Similar is the case for Prandtl number, which also had surfaced earlier. The newer entities are coming next, the Lewis number, which is essentially the energy transport caused by diffusion relative to thermal conduction, and the Eckert number, which for a calorically perfect gas happens to be an expression like this, gamma minus 1 m square. So, it is actually connected with gamma as well as m of the flow. However, the interesting point to note over here is that gamma and m did not come out to be one of those similarity parameters like they did in the compressible non-reacting boundary layer case. So, non-reacting compressible boundary layer flow had these following similarity parameters, as we took note already that Reynolds number and Prandtl number are the common factors, while gamma and m infinity was found in the non-reacting boundary layer, while they have not surfaced explicitly, but through the Eckert number over here. Additionally, Lewis number has been identified as a new similarity parameter. In the reacting boundary layer, gamma and m lose their significance. Instead, they are replaced by Eckert number. Gamma and m are not similarity parameters in a viscous high temperature chemically reacting flow, which needs to be taken into account. Additionally, due to chemical reactions and the associated concentration gradient of species, diffusion becomes an important phenomenon, and therefore, Lewis number gets introduced. Reynolds number and Prandtl number are relevant for both cases. So, we summarized here once again. Next, we move on to discuss a little bit about the boundary conditions. When solving the boundary layer equations, appropriate boundary conditions have to be imposed. It goes without saying, because ultimately we are solving a set of coupled partial differential equations. At the wall boundary, we have to have the wall boundary conditions. From the velocity boundary condition point of view, because it is a viscous flow, the no slip condition, which is relevant for viscous flow, has to be imposed. Now, we have two possible cases over here marked as A and B. Let us see what they are. In A, we have, if there is no porosity in the wall, therefore, there is no possibility of transpiration of a gas through the porous wall in or out of the wall. Additionally, if there is no ablation due to high temperature, that means the wall is not getting eroded or chemically reacted and therefore depleting due to high temperature effects, then at y equal to 0, u and v both are equal to 0, leading to 0 mass transfer essentially. This is one possibility. The other possibility is if the conditions at the wall are different from those mentioned in A, then at y equal to 0, u equals to 0 will still be consistent. However, there would be a non-zero value of the v component, which is essentially the wall normal component. So, what we are talking about over here is that the wall exists along the x direction, the wall normal direction is y, the y equal to 0 basically defines the wall. You have a boundary layer formed on the wall like this, and you are talking about imposing boundary condition at any point on the wall. So, if there is some kind of a flow normal to the wall, then you will have a v which is not equal to 0, and the subscript w of course is standing for the wall itself. Coming to the temperature or thermal boundary condition, if it is an isothermal wall, the wall is maintained at constant temperature. So, T is equal to T wall, in brief written as T w. For an insulated or adiabatic wall, the heat transfer should be 0. So, we write down the heat transfer expression which we had described in an earlier lecture in this week. So, for a binary gas mixture, the DIM will be simplified to D12, and the Q essentially when it goes to 0 means that for a binary gas mixture, the above equation will reduce to this form, which means we cannot directly impose the condition del T del y at the wall equals 0 like the way we have learnt earlier in the case of non-reacting compressible boundary layer. So, the adiabatic boundary condition which we are generally so familiar with is essentially for a non-reacting boundary. If reactions take place, then the boundary condition looks quite different. One part of the boundary condition is the energy transport by conduction, the other part is the energy transport by diffusion. The sum of the two should go to 0, and that is basically the boundary condition we have to impose in the case of an insulated or adiabatic wall for a reacting situation. Boundary condition for mass fraction of species I. So, since we are talking about a chemically reacting flow, we have to also talk about mass fraction of the different species, and how do we impose boundary condition for them. The boundary or the wall can be made of a material that tends to catalyze or enhance chemical reactions at the surface, and in that case such a wall would be called as a catalytic wall. When the wall has an arbitrary degree of catalyticity, the chemical reactions would proceed at a finite rate at the wall, and if W dot C is the catalytic rate at the surface, then W dot C I is the mass of species I lost at the surface per unit area per unit time. This is due to the surface catalyzed chemical reaction. Therefore, the particles of species I are fed from the gas to the surface through diffusion process. The diffusion flux to the surface element of area dA would be given by a form like this. The negative sign associated with a downward movement of the diffusing species towards the wall, and then we can invoke the Fick's law to write it in this form, where the gradient of C gets involved. This being a binary gas mixture, we bring in the diffusion constant or coefficient D12, and thereby we end up getting an expression for the W dot C for a particular species I. The subscript W basically means that we are at the wall, that means y equal to 0. So, this equation basically defines the gradient of the mass fraction of the species at the wall. It is obvious that for a non-catalytic wall, this W dot C I would be 0, and hence the gradient of the mass fraction will go to 0. For an equilibrium catalytic wall, on the other hand, the boundary condition will be given by C I equal to C I equilibrium. In that case, chemical reactions are catalyzed at an infinite rate, so that you are always at equilibrium conditions. So, the mass fractions at the wall are their local equilibrium values at the local pressure and temperature which exists at the wall. There are 3 boundary layers which we are talking about in this kind of a flow, which coexist. In the case of non-reacting compressible boundary layer, we talked about 2 possible boundary layer thicknesses, one being the velocity or hydrodynamic, the other the temperature. However, here it is not only that due to velocity and temperature, but it is also due to species, which we will call as delta C. And the far field boundary condition is that at the edge of the velocity boundary layer, you should reach a value of UE. At the edge of the thermal boundary layer, T should reach a value of TE. At the edge of the species boundary layer, the mass fraction at the edge of the boundary layer means the free stream conditions would have to be restored. Let us conclude saying that in this lecture we recapitulated the Navier-Stokes equations for chemically reacting flow. We saw the different forms of the energy equation with different significance. The boundary layer equations for chemically reacting viscous flow were discussed. The relevant similarity parameters were shown. and the boundary conditions for viscous chemically reacting flow were discussed. Thank you.